Okay, so your data link layer is responsible for communication between end device network interface cards, so NIC to NIC communication. It allows upper layer protocols to access the physical layer media and encapsulates that layer 3 packet, which is either going to be an IP4 or an IP6 packet. When it comes down to the data link layer, it gets encapsulated into a layer 2 frame. So your upper layer protocol is completely unaware of the type of media that is used to forward the data. Data link layer does not care what type of medium we are utilizing, okay? It also performs error detection and rejects those corrupt frames as we talked about before. So in our computer networks, a node is a device that can receive, create, store, or forward data along a communication path. It can be either an end device, such as a laptop or a mobile phone, or an intermediary device, such as an Ethernet switch. So don't forget, end devices, examples are PCs, PCs, scanners, printers. Intermediary is a device that goes between the source and the destination. So something like a router, a switch, a repeater, those are intermediary. So think of intermediate just as it is, in between. Okay, so if I drew a network up here, this is my end device, this is my switch, and this is my router. Okay, even if I would go into someone on the same local area network, also an end device, I am going through an intermediate device. Which would be my switch for local area communication. If I'm going out to the internet, I am still going through both my switch and my router to get out. So your router is also an intermediary. Okay, so get a good understanding of the differences between the two. Now, without the data link layer, network layer protocols such as your IP would have to make provisions for connecting to every type of media. That would exist along path. So from source to destination, IP, which is the main routing protocol for the internet, would have to stop, encode, de-encode, encode, de-encode. Your information would never get there. So when we think about IP and that protocol, you want your information to flow as quickly from source to destination. Okay, so IP, either 4 or 6, simply says, just get it toward the destination. Now, 802 LAN and MAN standards are specified, or specific, to the type of network. So either Ethernet, WLAN, or WPAN. So Ethernet is wired. So we'll concentrate mostly on these two. And then this is your wireless. Data link layer consists of 2 sublayers. So it consists of the logical link controller and the media access layer. So when we think about the standard of Ethernet, Ethernet is the standard for local area networking or WLAN networking, as well as PAN. We're going to concentrate on these two. So Ethernet is broken down into different standardizations. Ethernet in its totality, the entire standard is IEEE 802.3. These you have to know. WLAN, we talked about wireless a little bit right before. So WLAN is 802.11. WPAN 802.15. Does anybody remember what that one was? We also had 802.16, if you can remember what that one was. And I think 802.15.4. Anybody remember from our past discussions what those are? Okay? Remember when I talked about wireless, we don't delve deeply into wireless, but you definitely need to know the differences between these standards. Okay? So 15 is your Bluetooth. 16, I'm going to get these two confused. One is WiMAX and one is Zigbee. I'll have to look at that. I think this one is WiMAX. And this last one is Zigbee. So know the different standards, okay, for your wireless communications. So here's my network layer protocol. So as encapsulation is happening, and we've talked about this a few times, what would be my PDU at this layer? What is my protocol data unit at this layer? IP is the protocol itself. What is that protocol data unit?
Branch socks, I think, might be wrong, but wouldn't it just be the data packets itself?
It would be the data packets itself. So I drop the word data, Mara. It's going to be packets. Okay? So data happens at the application presentation session. It's referred to as data. So these are just what they're referred as. It is a data packet, you're absolutely correct. But these are just what we call them in industry type of thing.
The word we use for it is just a packet.
A packet, correct.
That is what is transmitted over the network, even though it is a packet that contains data. When we're talking networking, we're not talking data packets, we're talking packets that contain data, which is a distinction without much of a difference.
And what I didn't want to delve that deeply into.
Say that again.
Thank you for that. Very good description. Now, your data link, what is my PDU there? We have to know these. And what is my PDU at the physical? Bits, we got that one. Okay. Frames, thank you. Okay. Now, your LLC sublayer communicates between the networking software at the upper layers and the device hardware at the lower layers. I'm going to talk a little bit more about that as we go along. It takes the network protocol data, which is our packet of information, and it adds layer 2 control information to help it deliver the packet toward the destination. Does anybody remember what the headers are for the network layer and the data link layer? It's like a kind of little review. What would our header be here? So a header can be defined as I'm going to say what needs to be included for identification by a particular device. What needs to be included. So think about our post office example that we looked at. Okay. In the network, what do you think, or at the network layer, what do you think your header of information should be?
Source IP and destination IP.
Source and destination IP, correct. And who lives at our data link layer? What device?
MAC address?
Nope. The other one. Who uses IP addresses to make forwarding decisions?
Routers.
Your routers. Okay. So your router lives here. What's that?
I could not think of the word for a second.
What'd you say?
I gotta think of the router for a second.
Oh, that's fine.
It starts with an R.
That's fine. And so at our data link layer, what would our header of information be? And what device lives here?
Switch to
Yeah,
would it be the MAC addresses for that?
correct. Source and destination max. And this is where our switch lives. Okay? I'm going to talk about this over and over and over again. Now, your MAC sublayer is responsible for data encapsulation and media access control. So we're going to talk about two different access control methods dependent on whether we're talking about a wired network or a wireless network. So your MAC sublayer controls the NIC and other hardware that is responsible for sending and receiving data on the wired or wireless LAN or MAN. It provides data encapsulation, meaning, so we talked a little bit before about encapsulation, and I said when you get to the physical link layer, it is transmitted as a bit stream. So it takes your data and it puts it into a bit stream of ones and zeros, right? How do you think our device knows what the data is if it's simply a stream of ones and zeros? Go ahead.
Pretty much the same way that we're able to, the word that I'm looking for means figure out from, but I don't know what it is. The same way that we're able to translate Morse code
Yeah.
back into the text that was when.
It's encoding and decoding.
Yeah, pretty much, because we have a standard that is essentially, if this is received in this word, it means this.
I'm going to give you along the right path, Mark, except for the data network, it's going to be a series of 8 digits are going to identify when a frame starts. A series of 8 digits are going to identify when it ends. So one would assume if it starts here, and then there's a rambling of ones and zeros in the middle, and it ends here, one would assume that what is in the middle is our actual data. Okay? All right. Those are referred to as frame delimiters. So the framing process provides important delimiters to identify fields within a frame. These delimiting bits provide synchronization between the transmitting and receiving devices. Next, we have our addressing. So addressing provides source and destination addressing for transporting the layer 2 frame between devices on the same shared medium. And we already defined that as MAC addresses. Lastly, error detection. Who wants to wow me and tell me what they remember about error detection?
Bit put on the end,
What's that?
the bit put on the end.
It is on the end, so it is a trailer of information at the data link layer.
Snapshot.
Kind of snapshot. I think you used that terminology last time before, Sasha.
It's what's compared with what was said.
Correct, it's a value. What were you gonna say, Laura?
On a very high,
Yeah, high level.
high level, it's, error correction is the process of detection and sometimes, depending on the state, the correction of errors within the transmission of data. Because, obviously, detection is, in my opinion, more important than the ability to figure out what went wrong, because figuring out something went wrong in the first place is supposed to be fixing it. Anyway, usually as a trailing, value at the end, simpler programs or simpler things. We have just like, oh, the number of ones in the entire data stream that I sent you is supposed to be this amount of ones. And if you get a different amount of ones, then oh no, we have a problem, and ask me to go back again.
Correct. What were you gonna say?
Isn't it like a checksum?
It is a checksum. Yeah, it is a checksum. So remember now in our, although I understand exactly what you're saying, Sasha, with the snapshot. I get it.
Well, I had CRC cyclic redundancy check, trailer equals like snapshot to be compared.
So like when you're doing something like a virtual machine, you take a snapshot at that moment. Or you do, oh my God, I've done it so long in Windows, what is it called?
It's like the,
Snippet tool?
No, it's not snippet, it's when you take the current configuration. Restore point. So it's kind of like so, but this is an actual value. Go
Is
ahead.
it kind of like getting a puzzle and looking at the cover of the box?
Well, it's kind of like getting a puzzle and the box is supposed to have 1,000 pieces and it only has 984. So you have that puzzle that clearly stated there's 1,000 pieces in here. But if you were to count the pieces, you only have 984. So is that puzzle complete? No, it's not. So it's corrupt. So in the data world, it is in that. So again, here's our data. This is encapsulation. So our data is here. Application, presentation, session. And then here is our transport, okay, with the header, source and destination, ports. Then we come down to our network with a header, source and destination IP. Then we come down to the data link, and it is a header as well as a trailer, source and destination MAC, and the field is frame check sequence, FCS. In that is that value, which is a CRC value. So frame check sequence is a field in the frame. Held within that is that cyclic redundancy. Okay, that is the value. That is generated. So as a source of information, when a source generates a piece of information, it creates that CRC value. It places that in that field. At the destination, when the destination decapsulates the information, it checks its own CRC that it creates and compares it to the one that is in that field. If they match, it is considered a good frame and sent up to be processed. If they don't, it is dropped. It is considered corrupt. Bless you. Now, your MAC sublayer also provides media access control, which is allowing multiple devices to communicate over a shared half-duplex medium. Full duplex communications do not require this access control. So this is really for legacy networking, but you do need to still know it. So at each hop along the path, and in networking, a hop is defined as a route. So at each hop along the path, a route, it says it right there, I'm sorry. A router performs 4 basic layer 2 functions. It accepts a frame from the network medium. It de-encapsulates the frame. Now, why would a router have to de-encapsulate that frame? What does your router need?
The location where it's going.
Location where it's going. So it's here, right?
Yeah.
It needs a destination IP, doesn't it? Which is what Sasha was saying. So it has to unwrap. Now, if it finds a path toward the destination, it has to rewrap because we need to be completely encapsulated.
When it rewraps, does it ever drop its source IP, or does it bow on its own MAC address or anything like that?
No to the first, yes to the second.
So
Okay?
you can trace it back to where.
So that's it. So what happens is it does that whole rewrapping. Go ahead.
The way that I understand encapsulation so far is essentially that your computer grabs a packet that it wants to send and it packages it with the header and trailer that it needs in order to make sure the packet is formatted properly, and then sends it off down its either cable or wireless, and then whichever thing grabs it next, packs it into its own thing, giving it its own, like, hey, this is
Correct.
where I am, this is where I need to send it to, and
Yep.
it's now a box in a box, and then it becomes a box in a box to the nth power.
Correct.
And then when it finally gets where it's going, it's like, oh, okay, so it came from here to now to the thing.
Correct.
Just to make sure I'm reading, because this is router, not router.
Say again? This?
Yeah,
Router.
yeah, because I think router for some reason.
Oh, R-O-U-T-E-R, sorry. Yeah, so Sasha, what has to happen, you're correct. Except IP's not going to change. It needs to look at the IP. IP doesn't change. What changes is the MAC. So now it's going to rewrap it in a new data link with new source and destination MAC. And it has to put a trailer on it again with the new frame check sequence and the new CRC based on what it knows. And we'll go over that again a couple slides down.
Is this a tool that can be used for like, hiding and encryption and like bouncing around so many routers?
This is just a validity test.
It's just a-
Yeah, for the most part, yeah. Okay, so then it re-encapsulates and then it forwards the new frame on the medium. Now again, if this router does this process and it is simply not connected to anything else, what's it gonna do? Drop it, throws it away, can't do anything with it. If it were connected, and it has decisions to make, it says, okay, where do I put this? Which exit interface do I send this out of? So it's gonna choose one of these three. And again, if one of these three do not match, it is dropped. Okay. Now, we do have our organizations that we do have to have basic understandings of. So my data link protocols are generally not defined by what we refer to as request for comments. Does anybody know what white papers are? So white papers are kind of like what the information about the development of something. So a software engineer developed a package, not a package, an application or a service or something like that. Well, they have to submit these white papers explaining exactly what happens and how this is utilized. Okay? Much like you buy an actual application. You need to know how it works, right? Or a device. So that's what's referred to as the white papers. So within the data link layer standards, there are not white papers. Okay? The Internet Engineering Task Force, IETF, maintains the functional protocols and services for the TCP/IP protocol suite in the upper layers, but they do not define the functions and the operations of TCP network access layer. So your data link protocols are defined by your engineering organizations. So IEEE is the Institute for Electrical and Electronic Engineers. ITU is the International Telecommunications Union. ISO is the International Organization for Standardization. This guy is who created the OSI. So if you just flip those around, ISO created the OSI. It's a quick way to remember that. And then lastly, ANSI is the American National Standards Institute. Now, there are two different topologies you need to be familiar with. When I say the word topology, what do you think of?
Network layout.
Just in general in life,
Layout.
a layout, right? Did you say, what did you say, network layout? Yeah. And you said just a layout, right? So if a helicopter is flying around the neighborhood and snapping pictures, it's taking aerial topology, right? It's a map of whatever. So you need to learn about these two different ones in networking. First one is your physical. Take the word as what it is. Physical means I'm connected to something. So a networking engineer would have something that looks similar to this. Years ago, we used to refer to this as a cut sheet. But what a physical topology does is it shows the actual physical connections and how devices are interconnected. So I can see here, I identified all the different rooms. I identified the racks and the shelves and the servers. Okay? Now, years ago, I myself would have combined all of this with the ports as well. Okay? I would put everything in my physical. I could say that the Ethernet port over here was plugged into the FA05 or 6, FA06 port on switch 1. So go back to our description command. So if I'm in here on this switch on port 6, my description could be connection 2, web server, shelf 1, rack 2, room 2158. Again, your description is to help you. Okay, I don't have to get out of my seat, do I? I know exactly where that server is and what room it's in, okay? Now, the flip side to that is your logical topology. So remember, when we talk about the word logical, virtual, where is that done? If this is hardware, software. Okay? Think of logical, the word logical, the log, and the word virtual as software done. So virtual connections between devices using device interfaces and IP addressing schemes. Would you not agree that when you did your switch lab and you went into interface SV1 and you gave it an IP address and you gave it a subnet mask, you did that in software on the device, correct? Okay? So your logical is how your network is addressed. Okay, and you can go so far as to see off of router 1, G000 is connected to switch 3, G01. So that's what I would put in that description. On this router on G001, I would say directly connected to switch 3, G01, and you could even identify the subnetwork if you wanted to. Okay, so again, those descriptions are for us. They have nothing to do with switching or routing of the device.
It's a little sticky note, but.
It's a sticky note, but in there, yeah. Now, we talk a little bit about WAN topologies. Please understand, you do not need to know how to configure these. They just bring them up here. I'm never really sure why they bring them up here because we're not going to do anything with them. But if you have a question regarding WAN topologies, these are the three that you want to know. Point-to-point is the simplest and most common WAN topology. It consists of a permanent link between two endpoints. So what does that mean? From point A, it is only ever going to go to point B. From point B, it's only ever going to go to point A. Okay? Nowhere else, nothing in between, point to point. Hub and spoke. Similar to a staff topology, where a central site interconnects branch sites through point-to-point links. So, here's my central site. Excuse me. Branch 1, branch 2, oops, leave it like that, branch 3, and branch 4. So everyone is connected to the central office. What's one thing you might see problematic with this topology?
Single point of failure.
Single point of failure. Central goes down, nobody gets networking. Okay? Okay. So in that case, we could do something like this, a mesh topology. A mesh provides high availability but requires every end system to be connected to every other end system. You might see something like this in the backbone of your network. Okay, so that if anything goes down, you have a redundant path ready to come up. Okay, so everyone is connected to every other device. Okay, so if any one of those connections go down, there is another way to get there. So redundant paths. Oh, thank you. So within your point-to-point, it is a physical point-to-point topology directly connecting two nodes. The nodes may not share the media with other hosts. Because all frames on the media can only travel to or from the two nodes, point-to-point, WAN protocols can be very simple. Okay? Now, even if you're looking at this picture and you're saying, well, they said point-to-point, and there's a network in the middle there, you can still have a point-to-point in a WAN situation. So what would happen in a situation like this, if I was using something like frame relay as my WAN protocol, and you don't need to know this, is FYI. Okay, I would go into router A, and I would say, it's a command line, I would create a map. And I would say, frame relay map, and this is not 100% correct, I'm not gonna write out the whole commands for you, this is just an example. Frame relay map. To get to B, use circuit 105. Now likewise, on B, I would say frame relay map. To get to A, use circuit 501. So you define it. So it's still only going from one to the other and then back the other way. Where are you going to put that circuit number? In your description. So you know exactly what it's connected to at the other end. Okay? Now, end devices on LANs are typically interconnected using a star or extended star. Star and extended star topologies are easy to install, very scalable, and easy to troubleshoot. This room right here is a star topology, is it not? All of us are connected to that one switch. That switch is our one point of failure. That goes down, we don't have connectivity, do we? Okay, now that switch is connected to that switch. Switch to switch. So extended. So if all of a sudden you have more devices in your network and you want to extend it out with another switch, that's an extended star. Okay, this in the middle of these is either going to be your hub for older technology or a switch for newer technology. Now, early Ethernet and legacy token ring topologies, or technologies, excuse me, provide two additional topologies. Be familiar with these. They are both considered obsolete, but you do need to be familiar with them. So a bus has all end systems chained together and terminated on each end. Again, what would be a parameter here that would not be helpful? That goes down, no one gets connectivity, right? In a ring topology, each end system is connected to its respective neighbor to form a ring. So they are daisy chained together in a daisy chain fashion. Does everybody understand what daisy chain is? So I take a hub, next to another hub, next to another hub, next to another hub. It's like making a necklace of hubs, daisy chained together. Okay.
Or else.
Say again?
Or else. The mythical snake that's eating its own tail.
Oh, gotcha. Okay, so in the earlier days, we used hubs. Now we are switch technology. So half duplex communication versus full duplex. So half duplex communication means only allowing one device to send or receive at a time on shared medium. Again, how do you understand shared medium? Okay. Think about it in this room. What is my shared medium? Switch, right? We are all plugged into this switch. This switch is plugged into that switch. That switch is where we gain internet connectivity. So shared medium. Okay? So hubs you will see depicted like this, or you will see them depicted like this. One-way communication. So what that means is, if this server is sending something to the hub, it has to be completely received at the hub before the hub can respond back. Now, full duplex communication allows both devices to simultaneously transmit and receive on a shared medium. So with our switches, we still have shared medium, but our switches are much more robust and much more intelligent. Okay? They are capable of sending and receiving at the same time. So simultaneous communication. So remembering when you did your cables, right? What did you do? You had transmit and receive. And this may not be phonetically correct, not phonetically, purposely correct, depending on whatever standard I'm looking at, so don't take it verbatim, it's just an example. And we had 1 and 3, and 2 and 6, right? Crossing over. So we could speak at the same time, 2 different sets of wires, no collisions. So within our access control method, we are going to talk about contention-based and controlled access. And we're going to use those 2 topologies that are the legacy topologies. So, in contention-based, all nodes operating in half duplex are competing for the use of the medium. Carrier sense multiple access with collision detection, CD, is for a wired network. Carrier sense multiple access with collision avoidance is for a wireless network. Controlled access is what we determine as deterministic. If this is 1, and this is 2, and this is 3, and this is 4, and by the very nature of a token ring, it says, while you have the token, you can send information. Now, if I'm talking about something with copper connection, my token could simply be the voltage signal that I have. So while I possess that voltage signal, I can send my information. And if 1 is done, so 1 would get the token first, 1 sends its information, when it's done, automatically goes to 2. If 2 has nothing to say, fine, it just passes it along to 3. But it is determined who is next in sequence. Used on legacy networks such as your token ring and your ArcNet. So again, this is my bus topology, and this is my token ring network. So let's break those 2 access methods down. CSMA-CD, used by legacy Ethernet LANs, operates in half duplex mode, where only 1 device sends or receives at a time. And it uses a collision detection process to govern when a device can send and what happens if multiple devices send at the same time. So if I'm on a bus, right, this is my bus topology, would you not agree that there are possibilities that 1, 4 could transmit at the same time? Perhaps 4 didn't pick up the signal that 1 was sending out. So they might transmit at the same time, they would collide.
If you've ever been on a Zoom call or any sort of conference call, and people try to talk at the same time, and you can hear none of them,
Yeah.
that's pretty much what happens.
Yeah. One silence, the other's out, the other one out. So it's just like you in an accident on a 4-way, right? Car 1, car 2, car 3, and car 4. 1 and 3 have a collision. What do? We wait, we get out of our car, we exchange information, we wait for the police, we wait until the police say we can go, and then we drive off in 2 different directions. Right? 2 and 4, they're not involved in anything, so they would probably be one of the next 2 cars that would flow. Right? Unless they're waiting for me, and I'm over here at this collision. So just like this in the data network, when 2 devices transmitting simultaneously collide on that shared medium, devices detect the collision. So let's talk about copper. So I have a copper connection, and we defined this in one of our first 2 meetings that we met, right? That a 1 is going to be equal to 5 volts, and a 0 is going to be equal to 0 volts. So if those are my parameters, what do you think a collision on the network would look like?
6.
Something above 5, right? Something unusual, something larger than the normal. That would be a collision. So each device would detect the collision. Now, again, just like we got out of our car, we took our insurance paper, we exchanged with our neighbors, they also do the same thing. Excuse me. They also do the same type of thing. What they do is the devices notice the collision, and they wait a random period of time before they will try to retransmit, even though they were not in the accident or the collision. That period of time is inherent to whatever operating system is on the device. Yes.
The hope is that by randomizing it, then we won't have a collision immediately after because each device will have a different random.
Correct.
set.
Correct. So what Mara is saying is each device would be set up, but like, even if it was a nanosecond difference, it's gonna be slightly different than everybody. You wouldn't have everybody in this room on the same time. Okay, you would have it slightly off so that there is not another collision.
Is it just generating, things so quickly that collisions, when they do happen, doesn't slow down the network?
Of course. Of course. Think of yourself, now go back to my accident. 1 in 3 are in the accident, but if we block off those 2 exits or those 2 roadways, would you not? And 3 has to go, 2 has to go this way? Would you not agree that that's going to interrupt the traffic? Okay? So when you're thinking about these things, try to keep it in humanistic forms. Okay? You're in a collision, what happens? You stop, you wait, you exchange. They stop, they wait. Okay? And once their timer goes out, then they transmit. And as Mara pointed out, because those timers are just a little bit off from each one, a collision usually will not happen again. At that instance, or in that instance. Now, CA is collision avoidance. It is used, did I go through all the parameters? Hold on. Oh, can I go back on this thing? No, I can't. All right. CA, used by 802.11 WLANs, also operate in half duplex mode where only one device sends or receives at a time. Also uses what we refer to now as collision avoidance to govern when a device can send and what happens if multiple devices send at the same time. So CSMACA uses a method similar to CD to detect if the media is clear. It uses additional techniques. So in wireless environments, it may not be possible for a device to detect a collision, right? It's out in the air. Can't necessarily detect anything. So what they do instead is they try to avoid a collision. So the transmitting device will include a time duration, informing everybody else on that channel that it is going to be sending information, and this is how long it's going to take for them to send it. Therefore, trying to avoid a collision. All other wireless devices receive this information and know how long the medium will be unavailable. And again, nothing is 100% carved in stone. Are there still collisions in the wireless network? Yes, but we try to avoid them. So the avoidance process simply states when a device is transmitting, they will include the time duration used for the transmission. Other devices on the shared medium will receive that time duration and know how long the medium will be unavailable.
It's essentially someone saying, hey, I'm going to use the phone line for the next 20 minutes. We got to make an important phone
Exactly.
call. Don't try to use anything else. So.
Exactly. Yep. Like when I'm using my AOL, kids, don't pick up the phone because you're going to bump me out. So let's talk a little bit about your frame. Data is encapsulated by the data link layer with a header and a trailer, which is what again? What parameters are your header and trailer in your data link layer? Source and destination what? MAC addresses. Data link layer. Data link layer. Frame. When you're talking about frames, guys, MACs. When you're talking about packets, IP. Okay? I will drill this into your head all semester long so that you will have the understanding. Now, your data link protocol is responsible, as I said before, for NIC-to-NIC communication within the same network. What does that mean to us? Within our LAN or WLAN, period. It has three basic parts. It has our header. It has our trailer. And it has our data. The fields of the header and trailer vary according to data link layer protocols. So what they're showing you here in this picture is I can start out here in an Ethernet type of situation. I can get to this router, and this router is using satellite. This router is using something different. This router is going back to satellite. This one is going back to Ethernet. That's that encoding and decoding based on the medium.
Sorry, I'm just
No,
trying
don't.
So when a header and a trailer are attached to the data,
Mm-hmm.
they're framing it.
Yeah.
That's why it's called frame.
Correct.
I was thinking like a frame.
Encapsulation is wrapping up of data, right? Mara kind of used the example earlier, but I'm going to use it again. Okay? I want to surprise my girlfriend.
Think of it like back when you get together.
I'm just going to say that. Let me talk for once.
No. You said like I didn't do this as a point to my dad around Christmas when I was like, what?
You did say a box. I give you credit for that.
To be fair, it was a box that easily 3 of me could have fit in,
Yeah.
and we used it to pack a bunch of screwdrivers.
Here's my diamond ring. It's very beautiful, isn't it?
Yeah.
I have that in a small box. I put that inside another box. I put that inside another box. And I put that inside another box. I give it to my fiance. They unwrap it. To get to here, they open this up and it's nothing. It's a box that's empty. They unwrap it. They get to here, yet another box that is empty. Or maybe if I'm nice, it's a box of chocolates. All in all, they're trying to get here. What is that data? The data is that ring, the original thing you're doing. Okay?
The packet refers to everything together as being sent.
That is correct.
And then the frame is just
At the data link layer.
at the data link layer.
Mhm.
Okay, so it's inside of that. Or it's a piece.
The data is inside of all of that.
Right,
Yes,
but a frame is a smaller piece of the packet.
correct. Correct. So the fields of the header and trailer vary again according to data link layer protocols. The amount of control information carried within the frame varies according to access control information and logical topologies. So this is kind of sort of what your frame looks like in depiction form. Okay, here's my packet, this is my data, right? So I know you just said packet, and you are correct, we do refer to it as a packet because IP is what's used on the internet. That's why it's confused. It can be confusing because it is an IP packet that goes on the internet, and that's because IP governs internet traffic, okay? So it is all considered one big IP packet when it's done. I just don't want you to get confused with this particular slide, okay? So, the reason why it's a packet here, Sasha, is because this is the networking layer, which you agree is above the data link layer. Okay? So, the network layer sends a packet of information down to the data link layer. Again, this data does not change. Okay? In this packet are my source and destination IP addresses. They do not change.
It's just compressing it.
Pretty much. Without using the term compression or anything like that, or zipping it up. Okay? Now, when we talked about that frame start and stop, okay? Here's my frame start. It's going to be a series of 8 bits that will identify that. My addressing is going to be my source and destination MAC. My type identifies my encapsulated layer 3 protocol. What's my layer 3 protocol? IPs. So type is going to be either IPv6 or IPv4. Control identifies flow control services. So control and flow control have to do with TCP. So when we talk a little bit more about TCP, we'll talk a little bit more about that. You will be doing under the Wireshark. So in looking at your Wireshark, does everybody remember underneath the Ethernet 2 portion of it, there was a little drop-down arrow like this, right? And if you drop down that arrow, you had code bits. And if you haven't done it, by all means do. We will do it again as we go along. So code bits. Meaning, if I were synchronizing means trying to bring up a connection. Okay? My synchronization bit would be set to 1. Now, all through your conversation, your synchronization bit will be set to 1 because you want that connection up for the whole entire duration, right? Now, say again? Presumably, yeah. Now let's say we're doing things back and forth up on this net, and now we're finished. And we have nothing else to do. We want to terminate. So now our fin bit would be set to 1. During synchronization and during communication, our fin bit would be 0 because we're connected, we're talking, we're conversating. Okay, so that's what they mean about those flow bits and flow control, things like that. Flow control, specifically to TCP, is how much information can be sent and how much information can be received at the destination. Again, your data contains the frame payload, what we are doing,
Would that be the same as bandwidth?
which,
The type of, or how much data can be sent? and how
No.
much can be received?
no, it would be, okay, you call me up and you say, Sean, I'm moving, can you help me with boxes? I go, sure, I can help you. I come over to your house and I say to you very proudly, I can carry 3 boxes at a time. And so I do, I start carrying my 3 boxes at a time. I go upstairs, I grab my 3 boxes, I come down, I load them in a truck. I go back up, I carry 3 boxes, I put them in a truck. Now I'm getting tired. I go back up, I can only take 2. I go back up, I'm really tired, I can only take 1. So what it is, and we'll talk about this more when we get to TCP, is source and destination agree on a byte size. How much information can I send that you can receive? That is flow control. And the flow control portion of it says they first agree, and then if the destination starts to get congested and can't receive all the information, it will automatically back off.
So it's adjustable.
Adjustable. It's a dynamic window. Okay, it is adjustable. Yeah. So that is that flow control portion. And then lastly, our error detection, our frame check sequence field, which holds our CRC value. So that is how our frame looks for us in the human network. Now, your layer 2 address has many different names. It can be referred to as a physical address because it is embossed on your neck. It is referred to as a burned-in address, and so some of you, when you did your switching lab way back when, and they asked you to find the burned-in address, coincidentally, the BIA is the same as your MAC. Okay, again, because it is burned into the NIC card. It is contained in the frame header, which includes the source and destination MAC address, used for local delivery only, so only on our local area network or our WAN network. Updated by each device that forwards the frame. So again, go back to what I stated before. For the beginner of the trip, this is my original source. First part of the trip, this is the source MAC. First part of the trip, So, we're gonna go over it in a couple of slides. So what happens is, when your source does that ANDing process that we're gonna talk about in a little while, its purpose is to find out if the end device lives on its own local area network, or if it lives on a remote network. If it lives on its own local area network, then the switch would handle that communication. If not, as you see in this example, if it's in a remote destination, which, if this is my original, and this is my final destination, and I'm going through two routers, which is essentially my LAN connection, right? Would you agree that that is remote? So a remote network means it's not physically connected. Okay? This is LAN 1. Oh, it's over here. This is LAN 2. This in between is your ISP. We have no idea how many devices that packet goes through, correct? Do you know what goes on in your ISP? I don't. We don't know what their connections are. Okay? But would you also agree that this source or destination is no way connected to this route? It is remote. And would you agree that this PC is not connected to that route? It is remote. Okay? If information is remote, then it has to go to my router. Specifically, where on my router does it go to? What is this interface called? How do I get out of my network? Default gateway. Now you need to go out. Nice of you to join us. Nice of you to join us. Oops, I tripped over myself. Okay, so your default gateway. So again, if it doesn't end in procedure on the same network, switch handles it. If it's going to a remote network, it has to go to the default gateway, and your router handles it. Is there somebody else at this door? Yes. You know what? Chance, just put the bucket in there. Hopefully, the cleaning crew is done making noise. Okay. So, from here to here is my first trip. So for the first frame, this is my source MAC, this is my destination MAC. This router does what this router does based on our previous slide, right? It unwraps it to get to the IP address. If it can deliver it, it rewraps it. When it rewraps it, it has to re-encapsulate it. So, a new, source MAC address, and a new destination MAC address. Now it goes to that router on that NIC. Okay, and this happens all the way through. MAC address changes. Because where's your MAC address? On the actual NIC card in the device. Okay, those router interfaces are NIC cards. Those Ethernet interfaces are NIC cards. Switch doesn't get involved in that. Okay, it's just the routers. Okay, so that's why MAC addresses change from point to point. Okay? So as the packet travels from host to router, router to router, and finally router to host, at each point along the way, the IP packet is encapsulated in a new data link frame. Each data link frame contains a source data link address of the NIC sending the frame and the destination data NIC or link of the NIC that is receiving the frame. Now, the logical topology and physical media determine the data link protocol that will be used. So, some data link protocols is Ethernet. Ethernet is the traditional technology for connecting devices in a wired local area network over or a wide area network. 802.11 wireless, a WLAN, is a wireless LAN using radio technology to connect your nodes. Point-to-point, PPP, is a WAN topology. Again, is a point-to-point, refers to a suite of computer app communication protocols that provide a standard way to transport multi-protocol data over point-to-point links. High-level data control, data link control, HDLC. It is a WAN topology or technology or protocol. Yeah. Protocol. It is a group of protocols or rules for transmitting data between network points, sometimes called nodes. And lastly, frame relay, also a WAN protocol. It is a packet switching telecommunications service designed for cost-efficient data transmission for intermittent traffic between local area networks and between endpoints. You will not configure any of these. Okay, these are CCNP topics. Okay, you guys are CCNA. These are CCNP topics. So a LAN typically will use a high bandwidth technology capable of supporting large numbers of hosts, relatively small geographic areas, a single building or a multi-building campus, and its high density of users make this technology cost effective. Flip side to that, using a high bandwidth technology is usually not cost effective for LANs because now you're covering a large geographic area. So, cities or multiple cities, for example, the cost of the long distance physical links and the technology used to carry the signals over those distances typically would result in lower bandwidth capacity. It would just be too expensive otherwise. How are we feeling?
A little hungry, to be honest.
That's okay, we're gonna take a break before we do the next session. So tomorrow I'm gonna try and upload this bad boy. We'll see how it goes so that you will have the capability to listen to it again. Okay? Thank you.
What's our policy on getting a classroom?